Okay, these are the, this is the quiz, chapter 9, chapter 10, and 11 quizzes. So let's go over the answers first. This is chapter 9. First problem, you should have got 1.71 kilogram meters per second of the units on that. 2, you should have got 855 newtons or 850 newtons, depending on if you're paying attention to sig figs or not. I'm sorry, this was 1B. And then 1C, you should have got the same thing, but in the opposite direction because of Newton's third law. Number 2, the energy before equals the energy afterwards. And so if you set up a system of equations, what you end up getting is the velocity of the thorium nucleus is about 359,692.3 meters per second. Now I know you could round that and pay attention to sig figs, but this is the answer I went with. Number 3, you end up getting 6.78 meters per second at 41 degrees north of east. Number 4A, you end up with 30,000 Newton seconds. B, you end up with an average force of 3,333.3 repeating newtons. And C, you end up with a change distance of 540 meters. All right, next is chapters 10 and 11 quiz. For number 1, you end up with 249 joules. Number 2, you end up with 126 watts. Number 3, you end up with 1.4 meters per second. Number 4, you end up with a velocity of 15.6 meters per second. Okay, first start with problem 2 on chapter 9. It says a single uranium atom has a mass of, let me copy this down real quick for you. So it gives us this information. Mass of the uranium is here, and then it emits an alpha particle. So what I did is I said, okay, energy before has to equal energy after. And in fact, I think it'd actually be best to do momentum, because we don't know if any energy is given off. So momentum before equals momentum afterwards. And so before, if you want to draw like a picture here, you start with the uranium, and then after, you end up getting an alpha particle flying this way, and obviously equal and opposite, so you're going to get a thorium nucleus flying the other way. So that's kind of like a little visual representation of what's going on. From there you can set up the equations. Beforehand, you have no momentum because nothing's moving. Afterwards, you have the momentum from the alpha particle, which is just mass times velocity, plus the momentum from the thorium nucleus, which is just mass times velocity. So then it's just a matter of plugging in. I'm going to pause it and just plug in the numbers. To find the mass of the thorium nucleus, you have to actually take the mass of the uranium and subtract the alpha particle, because that's what's left over. So that's going to be the tricky one to get, is by subtraction. Let me fill this out for you. So when you fill that out, you get this. This is the mass of the thorium nucleus after you subtract uranium minus alpha. And then if you solve for the velocity of the thorium nucleus, you end up getting the answer we got, 359,692.3 meters per second. Okay, so we have a blue car and number 3 traveling this way. We have a red car traveling this way. They're going to collide, and they're going to travel off together in some kind of a path like that. So what I'm going to do is I'm going to break this up into x and y momentum, and I'm going to do before, and I'm going to do afterwards. So if you look at the x momentum beforehand, it's simple. All I have is the blue. So that's the mass of the blue times the velocity of the blue, which I'll just fill that out now. Actually, I'll write the equation. And afterwards, I have the mass of both times the velocity of both in the x direction. Right? So I'm going to fill that out first. The mass, I'll fill that out for you. So this is what the equation you get. Fill it all out, and you're solving for this one variable. Velocity of both in the x direction, which gives you 12.66 meters per second. So now we're going to do the same thing in the y. This time beforehand, all we have is the red. So we have the mass of the red times the velocity of the red beforehand. And then afterwards, we have mass of both traveling off together times the velocity of both in the y direction. So if we fill this out, we get this, and then we can solve for velocity both in the y, which ends up giving us about 11.01 meters per second. Now we want to make a triangle because we're looking at this triangle here. We know the x component of velocity of both of them is 12.66. We know the y component of both is 11.01. We do the Pythagorean theorem to find the overall velocity in that direction, which is 16.78 meters per second. And we can do inverse tangent to find the angle, which is 41 degrees. So we would end up saying 16.78 meters per second at 41 degrees. And that'd be north of east. Okay, the next problem gives us a rocket that takes off. This rocket takes off from the ground. It obviously takes off with no initial velocity in the y, but it ends up reaching a maximum velocity of 120 meters per second after 9 seconds. So if we set up an equation for part A to find the impulse, we have one equation for impulse. It's F delta t equals the change of momentum. And we can use the change of momentum, which is mass final velocity minus mass times initial velocity. Final velocity we know is 120, so this is just 250 times 120. And this is 250 times the initial velocity is 0. So that's going to cancel out. So if we just do this, that gives us 30,000 newton seconds, which is the impulse. For part B then, the average force that the rocket has, we can just use this equation because we know that force times change in time equals the impulse, which is 30,000. So we can just plug in the time of 9 seconds divided by 9, and we can find the average force, which is 3,333.3 repeating newtons. That's accelerating this rocket upward. Part C, with the altitude that it reaches then, just use F equals ma to find the acceleration. If you do that, you end up getting the acceleration equals 13.3 repeating if you plug in this force and then the mass of the rocket. From there, you can use the final velocity equation. Final velocity squared equals initial velocity squared plus 2a bar change in distance. So we know the acceleration. We know the initial velocity is 0. And we know the final velocity it reaches is 120. Go ahead and solve for change in distance. And what you get is change in distance equals 540 meters. So in the next problem, we have two people pushing a box against the floor. One person's pulling at an angle of 40 degrees to horizontal, and the other person is pushing at an angle of 40 degrees to horizontal. So that's what the picture looks like. It's a little hard to draw at first. Some people had some hard time interpreting the English to set up the picture, which I know is the hard part. Once you get the picture, though, it's pretty easy because you can do work equals force times distance. But keep in mind the force that you're using has to be in the direction. So I'm going to have to use this red portion of that force, which I'll call the force in the x direction. So I'm going to have to set up a triangle. And I'm also going to have to use the force in the x direction 2 here. Those are the two forces I'm going to have to add together to use of the force because those are the only forces that are doing work. So let me find those with just simple cosine. You know, cosine of 40 equals adjacent f of x over hypotenuse 11.4. You multiply both sides by 11.4, that gives you this right here, which is 11.4 cosine of 40. I'll just leave it like that. Plus, and then this one is adjacent over hypotenuse again, so you end up with 11 cosine of 40 for this one. And you add them together, multiply by the total distance moved, and that gives you 249 joules. Okay, next problem says we have a force that goes from 204 to 44 in 16 seconds, and it travels a distance of 16.3. Now, if we want to find the average power, we know that that would equal work divided by time. That's what power is. But work is just force times distance divided by time. So that's what we're using, but we need to use the average force because we're talking about average power. So the average force from 204 to 44, if we add that up and divide by 2, that gives us 124 times the distance of 16.3 over 16 seconds, which gives us 126 watts. Next problem gives us a hemisphere, not a very good picture, but it goes from here to here. And we need to talk about how fast it's going here based on what we know. So we're talking about energy. We know that energy before has to equal energy afterwards. We know that before, all the energies and potential energy at the top, mgh. Afterwards, at this spot, it has both kinetic, 1/2 mv squared, but it also has potential energy if we call this our reference line, which we're going to do. I'm going to call this my reference line height 0. So that any height above that has some potential energy as well, gravitational potential energy. To find that height right there, I can use this, actually this would be 0.14, the radius. And I can find that height using sine as opposite of hypotenuse, so sine of 16 degrees equals, I'll call this y right here, y over 0.14, multiply both sides by 0.14, and that's what I'll use for my height right here, my height afterwards. Before, my height is just the radius, which is 0.14. So let me plug everything in real quick. All right, just plug everything in, you get this, and obviously you're solving for that velocity that it has towards the bottom, which you end up getting velocity equals 1.4 meters per second. You solve for that v. All right. The last problem then gives you this problem here, where you are going down the hill, skier's going down the hill, and he goes down this longer hill at a steeper angle, and then he goes back up an angle that's less than that and it's shorter. Okay, so we know that energy is conserved, so we know the energy before has to equal the energy afterwards. I'm going to call this before, and I'm going to call this point after. So beforehand, it's got all potential mgh, right? Because the skier starts from rest. Actually, I'm sorry, no. Beforehand, the skier does have some kinetic energy because they're moving. It says that they're moving with a horizontal velocity of 0.434 meters per second. So I'm just going to use that. Now, I know technically that, this is a little bit confusing, but technically there would be a different velocity down the hill right here. We can actually calculate that based on the angle and use that for kinetic energy because it does have vertical and horizontal. But I think that this problem just wanted you to use what they gave you for the initial kinetic energy, this speed. So beforehand it's got kinetic energy 1/2 mv squared, where we use this v, but it also has potential mgh. So we'll use this height for that. Call that height 1. Okay, and then afterwards I'll call this height 2. Oh, it's going to have kinetic, I'll call this v final, plus, and then mgh, where I'll call this h2. So we need to find those values. You need to use opposite over hypotenuse. So you need to use sine of 27.6 equals opposite over hypotenuse to find this height. And then same thing with this one. Use sine of 20.7 equals opposite over hypotenuse to find this vertical height. So I'm going to plug everything in, and you get, actually before I plug everything in, you'll notice that the m's cancel because there's an m in every term on both sides. So if you just factor out an m and then divide, however you want to look at it, all the m's cancel. So I'm going to get rid of that and simplify this a little bit. So you end up with this big long equation if you plug everything in. And then you got to solve for this variable, which is the final velocity. And in fact, I think that's squared. Sorry, that's squared. And so when you solve for that, you get a final velocity at 15.6 meters per second. What that means is it did reach this point with speed up here. If we would have got 0 for this, then that would have meant it reached that spot and stopped. And if we would have got a negative number here, then what that would have meant is it didn't reach this spot and came up short. Okay, so keep that in mind. But we did get a positive value, so we know that it reaches that spot with some speed, some energy left over.